Exercise 59, let's talk about p-adic representation of profinite group and the lattice. Let's first state this exercise. For any way p-adic representation of profinite group gamma, I will expand or recall the notations very quickly. There exists a gamma stable ZP lattice is denoted by lambda side way. Gamma stable means this gamma action acting on this lambda is still inside lambda, because in priori it's only acting on representation way, not on its lattice. But we claim there exists such a lattice, although not arbitrary lattice, of course. So we will start with arbitrary lattice and then by and something to still make it a lattice and make sure that the gamma action will not get out of it. So let's recall some some notations. Firstly, what is this p-adic representation of profinite group gamma? So recall the definition of p-adic representation of a profinite group gamma is firstly just as general representation theory or representation, so group homomorphism grow from gamma to some GLN of V so here let's say gamma finite dimensional cubic vector space with finite dimensional cubic vector space, and if you fix the basis, then this is just GLN QP. I suppose this dimension n, but not yet finished. We still require one more condition: rho is continuous. So with respect to the product topology here, product topology of p-adic topology on each QP component. Because this has a cubic vector space, just finite dimensional cubic vector space, okay? And some exercise. This should be equivalent to saying that gamma acting on way, two-way, is continuous. So again, here we have product topology. Here we have the product topology on way, because this is the cubic vector space. Again, product topology or p-adic topology on each QP component. Second thing, a lattice is following this statement of this exercise, which I mean, further explanation, this lambda is a finite free ZP module such that extends scatter to QP gives isomorphism of QP vector space. Thirdly, let's recall what are the opens of QP? The answer is the opens of QP are all of the form p to the power n ZP for some n. Integer. Okay. So notice that it's not finite index. The reason that there's no surprising because this is not compact, but only locally compact. This was proved. If you go look back, exercise 57, 58. And actually, those are compact. We also prove that CP is compact, and so multiplication by p to the power n, or this is like a translation. Multiply by with any element, it would give you homomorphism from the domain to its image. And so this is compact opens. Actually, all the opens, open subgroups. Sorry, what I mean, open subgroups of QP. That's what I'm asking. Right. And small remark is that notice QP quotient ZP. So this is discrete. It's not finite, but it's discrete. Basically, any element x bar. So notice that x plus ZP is an open neighborhood of x. And so after you do the quotient, this is the singleton is open sub. This is this discrete topology here. Although it's not finite index, but ZP is open in QP. QP is not compact. So because when QP is so in general, if you compact and if you have an open subgroup, then it will be finite index because the union with its cosets give you a covering, and so it must be a finite covering by the compactness. So let's go to the proof. So let's denote this continuous group homomorphism from gamma to automorphic group. Okay. Fixing QP is a representation. Continuous group homomorphism, and just start with an arbitrary lattice, let's say lambda 0. Let's say p lattice. And then just notice that lambda 0 extend scalar to QP. This is isomorphic to weight. And so if you have some automorphism over gamma 0, just extend QP linearly. This gives you automorphism on weight. So notice we have this, hence the automorphism of gamma 0 fixing ZP naturally embeds into automorphism of weight fixing QP, and moreover this is open. This is an open subgroup because we're talking about product topology, right? When we're talking about that topological space, think of this as GLN of say P after you fix the basis, and this is GLN of QP homomorphic. And then talking about the product topology. And so ZP is open on QP, and so product of those ZP would be a product of open, and hence an open under the product tautology. This is open. Hence, in particular, gamma is profinite and hence compact. Implies not yet. We haven't constructed really. I want to say open subgroup of gamma would be finite index, right? But not yet gamma. So hence, if we consider the inverse image of this open, so this is in gamma. Again open because rho is continuous, and it's finite index. As gamma is compact. So let's denote this by gamma 0. So this is open gamma, and the index is finite. Right, so what can we say now? Our problem was that if you just look at your lambda 0 and you have your gamma 0 which fixes it, but if you look at your big gamma action, it's not necessarily fixing lambda 0, but how far is it? Notice it's just, if we collect all those cosets, and then you could just write it as a union of those gamma I. So let's say gamma I in some gamma, where let's say gamma is a set of finite set of representative of cosets. Cosets of gamma with respect to gamma 0. Okay, and then now how far is it? So any element is of this form, so gamma 0 doesn't change anything. You only have to make sure gamma I still fall into some lattice. So we just define our new lattice gamma to be, because each element of big gamma is automorphism of wave, which should turn gamma 0 into still a lattice. So how is it this gamma I acting through rho? That's the definition. And if you just add them together, right, finite to many I, then this is again lattice, because it's a finite sum of lattices, again lattice. But now it is gamma stable. And so we are done.